During a rare and precisely defined alignment, 3-eye Atlas was observed under conditions that eliminated shadow, distortion, and most perspective effects. The interstellar object lay almost directly along the Sun-Earth axis, placing Earth within less than a single degree of its forward-facing geometry. In that narrow observational window, images from the Hubble Space Telescope revealed a dust structure and emission pattern aligned directly toward our planet. This orientation was not inferred or stylistic. It followed from measurable geometry, illumination, and projection. For the first time since its discovery, 3-eye Atlas was not seen in passing or from the side, but face-on, with its dominant structures presented along the Earth-Sun line. What emerged in those images was not a diffuse chaotic coma, but a clearly defined antitail and a set of discrete, symmetrically spaced jet-like features. Such structure is difficult to reconcile with purely random outgassing, particularly for an object entering the solar system for the first time. Whether these features reflect an unusually ordered nucleus, a specific rotational geometry, or dust dynamics not yet fully understood, the alignment exposed details that standard comet observations rarely reveal, and that raise questions current models do not cleanly answer. The observational conditions that made this possible were unusually strict. The alignment placed Earth almost exactly between the Sun and 3-eye Atlas, reducing the phase angle to near zero and producing a strong opposition surge. In this configuration, shadows on dust particles largely disappear, and backscattered light dominates the observed brightness. This effect does not merely make an object brighter, it changes what can be seen. Features that are normally masked by contrast effects or angular scattering become sharply defined. For most comets, this kind of alignment is routine and well understood. For a fast-moving interstellar object on a hyperbolic trajectory, it is exceptionally rare. The images were captured by the Hubble Space Telescope in a sequence of long exposures timed precisely around the alignment. Standard image processing techniques were applied to enhance contrast and reveal faint structures, but no non-physical elements were introduced. The resulting frames showed a coma that was both bright and internally organized, with features that persisted across multiple exposures. This persistence is important. Transient artifacts or processing errors tend to appear inconsistently. What was seen around 3-eye Atlas remained stable over time, indicating that the structures were real and intrinsic to the object. One of the most prominent features was the antitail. In comet science, an antitail is not a reversal of direction, but a perspective effect. It forms when large dust grains released earlier along the orbit remain close to the orbital plane and are viewed edge-on. Under the right geometry, this dust appears to extend toward the Sun rather than away from it. Antitails are known, but they are uncommon and typically faint. Their visibility depends on a narrow combination of dust size, emission timing, and viewing angle. In the case of 3-eye Atlas, the antitail was not only visible but sharply defined, appearing during the precise window when Earth lay almost directly along the orbital plane. The prominence of this antitail implies a population of relatively large dust particles. Smaller grains are quickly pushed away by solar radiation pressure, forming the familiar broad tail that streams away from the Sun. Larger grains move more slowly and stay confined near the orbit. Producing a visible antitail, therefore, requires either sustained emission of large particles or a release event capable of ejecting them coherently. For a comet making its first close approach to the Sun, this raises questions about surface cohesion and internal structure. Loosely bound aggregates tend to fragment chaotically, producing a wide range of particle sizes and diffuse emission. The clarity of the antitail in 3-eye Atlas suggests a more controlled process. Equally striking were the jet-like features emerging from the inner coma. 3 distinct structures were visible, separated by approximately 120 degrees. Jets in comets are usually associated with localized active regions where sunlight heats volatile material, causing gas and dust to escape. As the nucleus rotates, these jets sweep through space, creating curved or spiral patterns. Perfect symmetry, however, is rare. Active regions are typically unevenly distributed, and rotation axes are often tilted in ways that break regular spacing. In 3I Atlas, the jets appeared evenly spaced and relatively straight, at least under the alignment geometry. This symmetry invites a rotational explanation. A rotating nucleus with three dominant active regions could, in principle, produce jets separated by roughly equal angles. But such an arrangement presupposes a degree of surface organization that is unusual, especially for an object of interstellar origin. Interstellar space is a harsh environment. Over long timescales, cosmic rays, micrometeoroid impacts, and thermal cycling tend to erode structure and increase randomness. An object ejected from another planetary system would likely experience additional stresses during ejection. That 3I Atlas appears to retain coherent, evenly spaced active regions suggests either an unexpectedly robust internal structure or a formation history unlike that of typical solar system comets. The orientation of these features relative to Earth is what gives rise to the language of aiming. During the alignment, the antitail and the apparent axes of the jets were projected along a line close to the Earth-Sun axis. This does not imply that the object changed orientation to face Earth. Rather, it reflects the fact that Earth happened to occupy the direction along which these features were most clearly projected. In astronomical terms, this is a matter of line-of-sight geometry. Yet the coincidence remains striking. At the one moment when shadows were eliminated and structure was most visible, the object's dominant features were oriented directly toward the observer. It is important to separate trajectory from orientation. The path of 3I Atlas through the solar system is well constrained by astrometric data. It follows a hyperbolic orbit, confirming that it is not gravitationally bound to the Sun. There is no evidence of propulsion, thrust, or course correction. The object did not alter its trajectory during the alignment, nor did it exhibit non-gravitational acceleration beyond what can be attributed to outgassing and radiation pressure. The sense in which it aimed at Earth is strictly optical and geometric, not dynamical. Even so, geometry matters in science because it determines what information is accessible. Many cometary mysteries remain unresolved precisely because we rarely observe objects under ideal conditions. Most data are collected at oblique angles, through varying phase geometries, and with incomplete coverage. The January alignment removed many of these limitations. By placing Earth almost exactly behind the Sun from the object's perspective, it created a natural experiment. The result was a view that minimized ambiguity and maximized contrast for certain features. What that view revealed was an object that looks less random than expected. 3I Atlas was discovered on July 1, 2025 by the Atlas Survey System, which is designed to detect near-Earth objects and transient phenomena. Its interstellar origin was quickly established based on its inbound velocity and orbital parameters. It became the third confirmed interstellar object ever observed, following 1I Oumuamua and 2I Borisov. Each of these objects has expanded the boundaries of cometary science. Oumuamua lacked a visible coma, yet showed non-gravitational acceleration, prompting debates about its composition. Borisov looked more familiar but displayed unusual chemical abundances. 3I Atlas now adds another data point, one that combines visible activity with structural order. Comparisons with solar system comets are instructive but limited. Most comets we observe formed within the same protoplanetary disk and share similar evolutionary histories. Their compositions, structures, and activity patterns reflect those shared origins. Interstellar objects, by contrast, are samples from other planetary systems. They may have formed around stars of different types, under different temperature and radiation conditions. Expecting them to behave exactly like local comets may be an unwarranted assumption. The features seen in 3I Atlas could be typical of interstellar comets, or they could mark it as unusual even among that population. With only 3 examples known, statistical certainty is impossible. The analysis and publication of the Hubble images were led by Avi Loeb, who has emphasized both the significance of the observations and the need for caution. The data, as he has noted, are consistent with natural explanations, but those explanations are not yet fully satisfying. The symmetry of the jets, the clarity of the antitail, and their alignment under opposition geometry all point to a level of internal organization that deserves closer scrutiny. Highlighting such features is not a claim of artificiality, it is an acknowledgement that existing models may be incomplete. One of the key questions raised by the data concerns the internal cohesion of the nucleus. Comets are often described as dirty snowballs or rubble piles, loosely bound aggregates of ice and dust. Such structures tend to fracture and erode easily. A more cohesive body, perhaps with a denser core or layered structure, could behave differently, producing more stable emission patterns. If 3I Atlas is more cohesive than typical comets, that alone would make it noteworthy. Its interstellar origin would then suggest that such structures can survive ejection from their parent systems and long journeys through space. Another possibility lies in rotational dynamics. If the object has a stable rotation axis and a relatively simple spin state, jets could remain fixed in orientation over time, creating the appearance of symmetry. Many comets, however, exhibit complex rotation, including tumbling and precession. Determining the spin state of 3I Atlas from limited data is challenging, but the persistence of the observed features hints at stability rather than chaos. Future analysis may constrain the rotation period and axis orientation more precisely, shedding light on this possibility. Dust physics also plays a role. The scattering properties of dust depend on particle size, shape, and composition. Under opposition geometry, certain scattering effects, such as coherent backscattering and shadow hiding, can enhance brightness and reveal structure. It is possible that the alignment amplified features that would otherwise be subtle, making the object appear more ordered than it typically is. Even if this is the case, the fact that such features exist to be amplified remains significant. The alignment did not create structure, it revealed it. What the data do not show is equally important. There are no anomalous energy signatures, no narrow-band emissions suggestive of artificial processes, and no deviations from expected thermal behavior. The object's brightness variations are consistent with dust scattering and outgassing. Its spectrum does not show exotic materials. In other words, nothing in the observations requires a non-natural explanation. But science does not operate on requirement alone. It operates on explanatory power. When standard explanations leave residual questions, those questions become the focus of further study. The timing of the alignment adds another layer of interest. The opposition event was brief, lasting only a short period before geometry shifted and shadows returned. Missing it would have meant losing the chance to observe these features under optimal conditions. That the alignment occurred at all was a matter of celestial mechanics, not design. Yet the coincidence underscores how much our understanding of transient objects depends on chance. How many interstellar visitors have passed through unseen or poorly observed because they never aligned in a way that revealed their structure? As 3I Atlas moves away from the Sun, its activity is expected to decline. Outgassing will decrease, the coma will fade, and fine details will become harder to resolve. Future observations will likely show a dimming object with less pronounced structure. The January data will remain the most informative snapshot we have. Analysis of those images will continue, with researchers modeling dust dynamics, testing rotational hypotheses, and comparing the object to both solar system comets and theoretical interstellar populations. The object's structure, revealed under rare alignment, happened to be oriented along our line of sight. That orientation exposed order where randomness was expected. It did not answer questions, but it sharpened them. Why does an interstellar object display such organized features? How common is this behavior beyond our solar system? And what does it tell us about the processes that shape small bodies around other stars? Science advances not by resolving every anomaly immediately, but by recognizing which anomalies matter. The January 22 observations of 3I Atlas matter because they push against assumptions about what interstellar objects should look like and how they should behave. They remind us that our models are built on limited samples and that the universe often presents cases that do not fit neatly into existing categories. For a brief moment, an object from another star system aligned with Earth in just the right way to reveal itself clearly. What it showed us is still being understood.